Thank you everyone for coming, all this way out to this remote building. I'm glad at least a few people have made it. I'm Jon Pretty. I don't know how many of you work in the Scala community or work with Scala, but I've been doing Scala for about 13 years now. And I've spent my career doing lots of interesting, or at least I think interesting, experiments with Scala and sort of pushing it to breaking point a lot of the time. And today I'm going to talk about a library, a very, or maybe even framework, but it's a very, very tiny library that works with, provides asynchronous functionality to Scala with a nice API and a lot of safety. And I'll spend a lot of time talking about that, but actually the talk is not so much about the asynchronous framework. That's going to be the basis for the talk, but I'll spend more time talking about dependent types and how you can use them in Scala. So just do a quick poll around the room. How many people use Scala as your primary language? So about half, okay. How many of you have never used Scala? Never used Scala. So you've all used Scala, at least had some experience of it. How many of you have had some experience of working with asynchronous programming? Okay, so I think that was almost everyone. Great. So there's really only one idea in this talk. The idea is to use dependent types as they exist and to the extent that they exist in Scala to make writing async code safer. I'm going to talk about this framework, and I'm still a little bit nervous about calling it a framework because it's fewer than 40 lines of code. 40 lines of Scala that gives us one fundamental feature, which is safety over ordering. I'll explain what that means in a second. So welcome to the people who have just arrived and found the room. You didn't miss much. So when people talk about frameworks, a lot of the time they get asked questions like, "Does your framework do this?" or "Does your framework do that?" And I think the answer to a lot of these questions is often, "Okay, I'll go and add that feature." Whereas what I've tried to do is I've got this very lightweight framework, which is in many ways orthogonal to Scala the language. So my answer to a lot of those questions will be, you can implement that in the language however you want. All I'm doing is providing these guarantees of safety. So what do I want to do? What are the goals of this library? To make asynchronous code easier to write, and syntax isn't everything, but it is important. People want to have people want to be able to write code that is readable, that they can understand. They don't want to have to read through lots of boilerplate, or even to write lots of boilerplate. So these are important things when both reading and writing code. But in addition to that, I want to make it harder for you to write code which won't run. And when I say difficult here, what I mean is I want the compiler to stop you before you compile this code. I want the compiler to say, actually, no, this is impossible, change the code, and then maybe we can consider running it, but not before. So that's what I'm trying to do. I'm trying to encode using the tools we have available in the compiler, in the type system, the constraints we want to have on our system that we can reasonably know at compile time, things we can know certainly won't work, and make sure they don't ever get compiled. So I'm going to have an absolutely trivial example for most of this talk. It's not interesting, and I don't want you to be distracted by what this is doing. It's my simplest possible example of some asynchronous code. What we're going to do is we're going to take a number from standard input. So there's a blocking task which is requesting input from a user. That can be a long-running task. There's another task which will generate a random number. Now, I don't know how you generate the random number, but we're going to do that asynchronously, so we can generate several at the same time. And then we're going to wait until both of those tasks are finished and multiply them together. So I've removed anything interesting from the code there. It's doing tedious, boring stuff, and I want you to focus on the what's being provided by the framework. In reality, obviously, generating a random number could equally be replaced by some synchronous code, which does something much more complicated, more interesting. And I'm going to leave it for you to substitute that in. I don't want to distract you by the unnecessary details. And although there's only three in my graph of tasks, there's only three edges. What I hope is obvious is that these will compose. You can create a quite complex graph of dependent tasks. So let's say you wanted to do this using futures in Scala. Is anyone not familiar with Scala's futures? Feel free to raise your hand because I'm happy to just do a quick overview. No? Okay, so yeah. So futures in Scala. When you create a future, you give it a lambda, and it will immediately start executing that lambda, which might take a while, but it will return a value immediately, which is the future. Now, at any point after that, you can try to get the value of the future. It might succeed if the lambda has finished, if the computation is finished, or it might fail if it's not ready yet. So maybe you get an exception, maybe you get a value. So it blocks on a different thread. So it sends the execution to either a thread pool or what's called in Scala an execution context. And in your main thread that you create the future in, you get a response, you get a return immediately. It doesn't block. You're dispatching the work somewhere else. Does that make sense? Okay. So if we wanted to write this really trivial example using futures, this is one thing we might do. I don't know if I can you see my pointer there? So, okay. The thing is I can't see the pointer. So we create an input future, that is getting the input from the user, and that will wait until the user types something in on the keyboard and hits enter. We have another task, another future, should I say, that will generate a random number. I mean, that one will probably complete very quickly. And then we have the third one, which is using this future.sequence method. And what that does is it takes a list or a sequence of other futures, and it transforms the list of futures into a single future of a list, or a single future of a sequence. So it turns it inside out when they've all completed. So because it's a single future, it has to wait for all of the others to complete before it returns its single list value, which contains all of the values within that. So we can do that, and then once that future has completed, and a future is monadic, so we can map across it. So upon completion, we know, or we sort of know, that the values from these two dependent futures are complete. So they have values in there, and we can get them out. So this is how you would write it in Scala, the Scala concurrent library. Yeah. Why is get called twice? So yeah, I was going to say that. So we have the future, then there's the value inside the future, which is an option of a try of the value. So we get it. So given the future, we get the value. The value returns an option of a try. Option is so the first get will assume that the option contains a value and that it's not none. So that's unsafe. Well spotted. The next get assumes that the value was successful. The try was successful, so there wasn't an exception thrown. So we make that assumption again, and we get. So both of these calls are unsafe, and toInt is also unsafe, but we're going to ignore that for now. We assume that the user types in digits. So we've finally got the value we want out, and we have to convert it to an integer because it comes in as a string. And in fact the future is typed as a string, so that's kind of to be expected. Then we do the same thing with the random value, and then we multiply them together, and then the result that we get from this output value, if we wait for it. Now remember, all three of these are created instantaneously, more or less, and this one is dependent on these two. So when output has completed, so when we've awaited the result of output, and we will wait infinite time. This syntax here is part of Scala standard library, and it's a little bit verbose, I think, as a deterrent to people to say this code is going to block. We're going to make it slightly less easy for you to do the blocking. So try and do things asynchronously. I don't really care too much about that, but we wait for the result, and then at the end of this we will get an integer, which is a random number times whatever you typed in. It's not very exciting, but this will work. But I'm relying to a large extent on the guarantee that this input value was definitely completed. I could write this input.value.get outside of the output block, and that would fail because it would be attempting to get the value before we've waited for it, or potentially there's a race condition, but in the general case, this would not be safe. We only happen to know it's safe here because we carefully remembered to include it in this sequence here. We carefully mapped across the value here. So I'm not entirely satisfied with this. Now there's an alternative way with chaining futures together, where we, using the map method, same as before, in the previous slide, I actually threw away the value. I said I don't care what the value is, but I'm going to map across it. So essentially I was only taking the fact that these had completed and then using that as justification for continuing. In this slightly different version, I'm going to pattern match on the result. So given that I've got the input future and the random future here, I'm going to expect there to be an input value and a random value coming out of that. So if you remember, the future.sequence turns a sequence of futures into a future of sequence, and this is the sequence that's inside that. That's the result. But in order to make this work, I have to cast. This is really horrible code. Why do I have to cast? Well, by putting the future of string in the same sequence as a future of int. Actually, I'm sorry. I've got the cursor on my screen. And I'm showing you where to look, but you can't see it, of course, which is useless. With the future input in the same sequence as the future string in the same sequence as a future of int, these get converted into futures of any. So the type is lost because they have to have a union type or a least upper bound, and in Scala that works out as a future of any, which is not ideal because it means that later on we need to cast them back into whatever types we wanted. And that is, of course, unsafe. So these casts here are a little bit risky. If we change the order of input and random over there, then this would all break, and the compiler wouldn't help us at all. So again, not ideal. So there's also, you can also write this in a for comprehension style. This is everyone familiar with for comprehensions as a yes or a Yeah. So this is a way of using the monadic features of futures, and saying, where's the cursor? Do this, then do this, and then do this with those two values. Does anyone know of any problems with this? Yeah. Yeah. So the input and the random are not carried out in parallel. They're dispatched to a thread pool or an execution context, which is great, but the second one doesn't get dispatched until the first one has returned. So we're losing parallelism there. So in each of these three examples, there's something lost. Here we've lost parallelism, and it seems like these three options I've presented are forcing us to choose between the safety of the ordering, that was the first one, type safety, the second one, I had to abandon that when I merged everything into a single type in order to pass it through future.sequence. And here we're losing parallelism. So the question is, can we get all three?
Can't you move the future declarations out of the comprehension so they're dispatched before you find them inside of the comprehension?
So I could...
val input future equals future, val random future equals whatever, and inside the core comprehension, input gets input future, random gets random future.
And then put the results in a tuple or something. As in the result from sorry, my cursor. Input.
Dispatched outside, you do the four comprehension bindings sequentially, but that doesn't matter because you're waiting for them anyway.
You. Oh, I see. Sorry. Yeah. Yeah, that works actually.
It does have a weakness that you're adding more superfluous variables or values. It's like you can still
that's true, but it's I still think that's a reasonable solution. Yeah.
Better than the first two slides. Still a little more verbose than you would like, but
Yeah. No, sorry. That's yeah. This is lacking in that respect, and. Does it work in the general case? Sure, you do need the additional bindings.
Yeah, it's the common workaround. It's not invented here.
Okay.
There's a blog post by Victor Klang where he just you can use vals inside a code comprehension, but the first binding always has to be magnetic. So what the workaround is find underscore to
yes.
find them, so it's kind of ugly.
Right. Yeah. That's a limitation of full comprehensions. Okay. Well, this talk isn't about async frameworks. It's about dependent types. So I will. Thank you for that. I'll move on to the.
I didn't want to derail your talk, but
Well, I wrote these. I went back and. So the order I developed this, I wrote the framework, and then I went back and wrote the justification for the framework, which is these slides here. This justification fell short. Anyway, this is how you write it using my framework. So we have async blocks. These are a bit like futures, except they don't start executing immediately. The first two look very similar. The third one, what happens here is that we say that the output is dependent on the two previous async blocks, input and random. And what we then do is we provide it with a lambda, and don't worry too much about the. I'm doing it again with my cursor over here.
There's not much code on this slide.
Yeah. So ignore this for the moment, but essentially we're going to call get the input value and the random value inside this lambda block, and then we await the result. So it's not much different yet. And you may well ask, what is the point in this? And it's actually more interesting for me, not so much the code that does compile, but the code that doesn't. So if I made this small change, so if I forget to declare input as a dependency, this will no longer compile, because calling input in here is now a compile error. So the rest of the talk will be explaining how that works, more or less. Is everyone okay with the thing that I've shown here? Yeah.
You omit the params to still not compile, or does it close over?
Right. Okay. So let me show you my next slide, which answers your question. There's a subtle distinction, or maybe subtle, maybe not. There's a distinction between the unevaluated async object, the thing representing that asynchronous computation, and the value you get out of it. And it's these parens here. And the key thing is they only work. You can only apply these empty parens to one of these async objects if you are in a context where it is safe to do that. That is the safety guarantee that the library is giving you. So we're going off the slide a little bit, but there's nothing interesting on the right-hand side. So we can call the apply method inside the output block because there is an implicit env available. There is you can't see it so well there, but there is this env object here. And if we explicitly apply the implicit, this is what the code looks like. So I've put some types in here so you can see a little bit more what's going on. I'll provide more refinements on these types later, but
This is still simplified.
this is
Generic, not
async will be generic. Right now it is I'm just going to pretend it's some generic asynchronous thing. Generic in the
take parameter.
so it'll get a type parameter basically. That is what I'm trying to say. And we will so the env parameter gets applied here and here. So that is to say that the Scala compiler. Oh great! Time to install new software. Remind me later. Okay. So Scala's implicits they get pulled in whenever they're needed. So if you have a method which requests a implicit parameter of a certain type, the Scala compiler will go and look within scope for an implicit matching that type. There happens to be one defined in this block, implicit env, and it will get applied to these parameters here. So if you look at the definition for the apply method, this is the one that gets called on input and random. It's expecting an implicit env there. And what that will do is it will actually get the value out, but I haven't shown the implementation. Is that all okay so far? I haven't really explained why it works in some cases and not others yet. So the type parameters have arrived. at least partially. So the easy part is the return types. This one returns a string. This one returns an int. Nothing exciting there. But the question is, what type goes in here in place of these question marks? There's the definition of async below. And I'm also going to say that the env parameter has a type parameter as well. And this is going to be critical in working out which values get the env they want and which ones don't. So if you remember back to the slide where with the code that didn't work, I didn't declare input as a parameter to the post method, and the env could not be applied. There was an implicit search failure, so it couldn't find an appropriate env for that value. So how are we going to do this? Hello to the people who've just arrived. So what I actually want is some representation of something set-like. And I want that representation at the type level. Now, why do I do that? Why do I want that? Well, the compiler is running at the type level. It doesn't have access to the values yet, so it can't go and check whether a value has been completed. So we only have the type level to work with, and we've got these set-like things to represent the set of dependencies of each async task. And that's an arbitrary size set of dependencies. It might be a single value, it might be no values, it might be 100 potentially. Now, for every async value which I assign to a named value, a named identifier, there's a singleton type associated with that. So for input, there is input.type. Is anyone not familiar with singleton types? Again, thank you. Raise your hand. I will give you a very quick overview. A singleton type is the type that has only one value, namely that type itself. So conversely, if you like, every value gives rise to a type, which is its singleton type. So you assign a thing to a value in Scala, you immediately get a type available that the compiler is able to work with, to talk about, to do computations on, type level computations on. So for each of those async values, we do have a singleton type. Input.type, we've got random.type, and we later get output.type. And one thing we need to be able to test, again, at the type level, is this condition that the async task we're depending on is a dependency, is declared as a dependency. So the question is, how do we do this? What machinery do we have in Scala's type system to do this? Well, there's one very well-known way of doing this, which is to use h-lists. Or at least it's quite well known in Scala. But h-lists are they're linear. They're defined recursively in order to. Was that time? 5 minutes. Okay. I'm about halfway. They're defined recursively. They're not ideal. Whereas intersection types, sorry to speed up, they have a lot of the same semantics we want from sets. So the type A with B, at least in Scala's type system, is considered equivalent to B with A. There are some soundless issues, but we won't encounter them, and I can guarantee we won't encounter them. So they're considered the same type. A with B, or A with B with A, is the same as A with B. It deduplicates. As you might expect, that you have a type int, and you find the intersection of int with int. Well, it's just int. It's the same type. So this is kind of what we would expect. So we've got reordering and deduplication semantics. These are the same as sets. And you can observe that the type A is a supertype of A with B. The type B is a supertype of A with B. The type C is not a supertype of that. So we can use subtyping as a membership test for these sets, these type level sets, if we represent the sets as intersection types. And we can have an intersection of singleton types. Now you might think, well, if I have a type representing the single instance input and another one representing the single instance random, what does it mean to talk about the intersection type? Because obviously that'll be the empty set. There'll be no members of that. That doesn't matter. We don't need to have instances for the type to be useful. The type can exist, the compiler can talk about the type, it can do computations on the type without it ever needing to create an instance. It remains as a phantom type. So we can have types like int with string. There are no instances of int with string, but it's completely fine for the compiler to work with them. So that's, I think, quite nice in a way. It means we don't have to provide evidence that such a thing can exist. And they're useful. The types are useful as bounds. So we can make this type A with B a bound on another type. And I'll show you how that might work. So this is what the types look like when I've replaced those triple question marks with actual types. You can see that the dependencies of output are encoded in its type signature as an intersection of singleton types. The code is the same as the previous version of this, but we've now got that intersection type specified. And also inferred, and the type inference is very important. I don't want to have to write this as a user. I want the compiler to work it out for me. Now, in order to get this type inferred, the variance is important. So, while input.type is, in this example, always a supertype of this intersection, there's no guarantee that env of the environment of input.type is a supertype of env of input.type with random.type, unless they're covariant. So covariant means if env's type parameter is covariant, it means the type env of something behaves, at least with respect to subtyping, in the same way as the types themselves. And in order for this to work, we need to make sure that env is covariant. We indicate that with a plus to the dependencies type parameter there. If the subtyping works in the opposite direction, so if it gets reversed when it's in a type parameter position, that is called contravariance. Is that 2 minutes before questions or 2 minutes before time up?
Yeah, we're at 10 right now.
Okay, I'll go over into the questions. So we want to have these types inferred. We don't want to have to specify them everywhere. So I use a little trick in Scala, which is sort of walking the delicate line of what's possible with the language, I think. So you saw this post method, which takes a list of dependencies, each of which is some async type. Now, I've specified it here as the deps parameter with var args. So you can provide multiple dependencies in parameter position here, and it will infer a type deps accordingly. But if we just took the least upper bound, the lub of those dependencies, we get a type that is not useful to us. It's async of any, returning any probably. It's not what we want. We want this depth type to be inferred as the intersection, because we need to use that later on to provide the subtyping bound on the env implicit. And we need to do that with contravariance. Now this is the first step towards making the syntax quite nice. When we call the post method, let's say we wrap each of these parameters in a dependency. So we say new dependency. I'm explicitly specifying the type there. But we can create a dependency around input, around random, and then we can infer a type based on the contravariance of dependency, or the D parameter, which is the intersection type. If it was covariant, then we'd get a lub of those, but we're using contravariant, so the type we get is the greatest lower bound, and that is the intersection type. So that's fine, except this is incredibly verbose, and we really don't want to have to write all of this every time. We might as well just sort it out some other way. So we use implicit conversions in Scala to automatically apply that dependency wrapper around each parameter. So we request a type which is dependency, and we put an implicit conversion in scope which converts from an async type to a dependency type, and in the process wraps it. So this implicit I've called auto wrap. It takes an async, returns a dependency, and we have to be careful here. We specify the type explicitly to be the singleton type, because by default Scala doesn't infer singleton types. It will naturally widen to the sort of the next type up, which would be just the async type, because that's generally more useful. We're generally not working with singleton types directly. So we'll get the type we want, and the the type parameter on this async.post method will get inferred to be the intersection type, which is what we want. If you look at all the hidden syntax in there that is inferred by the compiler, this is pretty much the same as the 3 or 4 lines I showed you at the beginning, the first example from Impromptu. It's horribly verbose. All of these type parameters, all of these implicits. This is what Scala hides from you. And this is what it becomes. Now, I've said this is almost boilerplate free, because there's a piece of code, or there's something in here which annoys me every time I have to write it, which is this implicit env part of the lambda. It's the same every time. We know that whenever we use one of these, whenever we call the post method, that the lambda it takes will have an implicit environment. It'll be the same every time. So it's frustrating as a user of this library to have to write that. Yep, I've got 3 more slides. So in Dotty, we have a feature called implicit functions, which allows us to define, rather than specifying at the call site where that post method is called, we specify at the definition site that will be an implicit lambda, and we can simply omit the implicit env there. So we lose that boilerplate. So Dotty has hope to make this even neater. And this is, I think, shorter and safer than I think all of the examples that we saw on the first slide, even the full comprehension one.
That's the same as, I'm guessing, Martin's keynote.
Oh, did he talk about it? Yes, it is the same. Yes, I didn't go to his keynote because I've seen it a couple of times before, but it is exactly the same thing. Yes, these are implicit functions. Yeah. So now it all makes sense. Now here is the usage that I think Martin didn't really envisage, possibly, but you can, yes.
Do you have the analog of a future sequence where I have a list of asyncs and I want to get the sync list?
I haven't yet, but you could pretend you could.
Kind of strange. How would you do with the singleton types?
Well, I think you don't need that. I think the future sequence is not required anymore. You simply refer to you say I depend on these named
A
asyncs.
list of strings, I map it to the async of string and then I want.
Okay,
So,
we
yeah.
gotta start
So, yeah.
getting ready for the next person. So if you have more questions for Jon,
Yes.
he's gonna be around then.
I'll be around the rest. I won't be around tomorrow, but thank you.